Hi everybody. Today we're going to design and build a Milliohm meter that is capable of measuring low resistance from around 1 ohm all the way down to 0.1 of a milliohm with an accuracy of 0.1%. Now, most multimeters on the market today are not capable of measuring such low resistances. In fact, their lowest range is around about 200 ohms and their maximum accuracy is around about 0.1 of an ohm. So clearly they're not capable of measuring very low resistance. There are a number of high-end multimeters on the market and some dedicated Milliohm meters available, but they tend to be quite expensive and they're usually out of the budget of the hobbyist. So what we're going to do today is build our very own low resistance Milliohm meter. So let's have a look at how we're going to do that. Right, well here we can see the block diagram of the circuit I propose to use today, and basically what we're going to do is use a technique known as the 4-wire system for measuring very accurately the low unknown resistance. And the way we do that is that we use 2 of the wires to supply a very precise constant current source across the unknown resistance, and we use a second pair of wires to then measure very accurately the voltage drop across that resistance and then calculate the resistance using Ohm's law. Now the way we're going to do that here today is we're going to supply 100 milliamps through the unknown resistance, and that 100 milliamps is going to be generated by the linear technology IC, the LT3092, and that will be set to give you a very accurate 100 milliamp source. And the way we are achieving that is by clamping the reference voltage on the constant current source IC at 1.25 volts using a Precision Shunt Regulator, again a linear technology IC. In this case it's the LT1634, and the reason I'm using that is it's very, very low current. This can operate at 10 microamps, which just happens to be the current source in this particular constant current source IC, which has 10 microamps. So that will then clamp the reference voltage at 1.25 volts, and then together with a set resistor of 12.5 ohms, we will generate a constant current of 100 milliamps. What we'll then do is measure the voltage, the very small voltage, across that unknown resistance, and to do that we're going to use a precision differential amplifier, and this particular amplifier is one from Texas Instruments. It's the INA 106. It has built into it some laser trimmed precision resistors which set the internal gain of this amplifier at times 10. And you'll see why we do that in a moment. If, for example, we have an unknown resistance, let's say it happened to be 0.1 of an ohm, and we supply 100 milliamps through that unknown resistance, well, at that sort of resistance, we will get 0.01 of a volt, or 10 millivolts, using Ohm's law. Now clearly you can see from that we want to indicate that we're looking at a 0.1 or a 100 milliohm resistor in this case, but the voltage reading is giving us a voltage of 10 milliohms. So ideally what we want to do is multiply that by a factor of 10, so the actual voltage that we're reading at the end of the day is directly proportional to the resistance that we're looking at. So if we feed that into the precision differential amplifier that has a gain of times 10, the output voltage that's coming out there will in fact be 0.1 of a volt, or 100 millivolts. So you can see from that the reading on the meter will give you a direct indication as to the resistance that we're looking at. In this case it's a 0.1 ohm of a resistor, and it's giving us 0.1 of a volt reading on the meter, or 100 millivolts in this case. So that's a very easy way of getting a direct relationship between the resistance that you're looking at and the eventual reading that you're displaying. Now, to use this precision differential amplifier, we need to drive it with a positive or negative voltage source of plus and minus 10 volts. But the circuit we're using today is all being driven by a single supply of 9 volts using 6 AA batteries. And then we're feeding that into a low drop 5 volt regulator. In this case I'm using an LM2940. And the 5 volts is what's driving the constant current source. And we're also going to feed that into a little voltage converter IC, the Max 680. Now this particular IC is a charge pump voltage converter. It uses 4 capacitors and switching to generate a negative and a positive voltage from a single positive supply. And in this case we can feed 5 volts in and we can get plus and minus 10 volts out, which is ideal for our precision differential amplifier. Now the reason I'm also using the LM2940 in this circuit today is it's a low drop voltage regulator. It has advantages such as short circuit protection. It also has an internal built-in protection for reverse battery input. But the main reason I'm using it is because as we're drawing 100 milliamps in this circuit when we're checking resistance, you could drain the batteries down relatively quickly, and therefore we want the readings to be accurate even as the voltage does tend to drop on the battery. And the low drop voltage regulator only needs about half a volt across it to regulate. So even if the battery supply here dropped all the way down to 5.5 volts, it would still work accurately and give us our plus 5 volts out, which means the whole circuit here will be working accurately as well. So I think what we'll do next is we'll have a look at the more detailed circuit of this little project. Well, here's the full circuit for our project today. The input voltage to the circuit, as I said earlier, is supplied by 6 AA batteries, so that's giving us a 9 volt supply, which we're simply then feeding into a 5 volt regulator IC, the LM2940, and giving us our plus 5 volts, regulated 5 volts out for the remainder of the circuit. The plus 5 volts is supplying the constant current source IC, the LT3092, and it's also supplying a voltage converter IC, the Max 680 there, with the 4 capacitors on it. That's the charge pump converter, and that's giving us output of plus 10 volts and minus 10 volts on pins 8 and 4, and that's what we're going to use to feed the differential amplifier here, the INA 106. Just going back to the constant current source, that's generated from this IC, as I said, the LT3092, and to make sure that that is accurate, we're going to clamp the set pin on pin 1 to precisely 1.25 volts, and rather than use a resistor, we're going to clamp it with a little shunt regulator IC, the LT1634, which will be more accurate. And these, as I said earlier, these ICs can operate at 10 microamps. We have a 10 microamp constant current source inside this IC, which is then driving the shunt regulator there. So that's clamped at 1.25 volts. The way this particular IC works is that whatever voltage we have on pin 1, the feedback loop there ensures that pin 2 is also at the same voltage. So if we've got 1.25 volts on pin 1, we'll have 1.25 volts on pin 2, on the output pin there. And to generate 100 milliamps, which is what we want for this circuit, we simply need to put 1.25 volts across a 12.5 ohm resistor, and that will give us 100 milliamps. Now, what I've done here is to provide us with that resistance. You can use 8 100 ohm resistors, that'll give you exactly 12.5 ohms, but not to give us some trim, I have 7 100 ohm resistors in parallel there, all 0.1% resistors, and then the last resistor is made up of a 56 ohm and a 100 ohm preset, and that will give us some trim when we come to setting it up initially to set the 100 milliamps current. And that is the current that's then going to be used to supply across the unknown resistance. You see here I've shown in green. The resistance, once in circuit, you have the 100 milliamps flowing through it. You then get a small voltage developed across it, and that small voltage is fed into this precision differential amplifier circuit here, which has got an internal gain of times 10 due to the internal resistors of 10 and 100k, these laser trim resistors inside the chip, and that will give us an output voltage then which will be proportional to the resistance that we have here, as I mentioned earlier. Now, in order to give us some adjustment in terms of zeroing the differential amplifier prior to testing the resistance, what you need to do is short these two leads together to zero the output, so the output is zero. In order to do that, I'm using the facility there on pin 1 of the differential amplifier to feed in an offset voltage, and we're generating that offset voltage by putting 100k preset between the plus 10 volt supply and the minus 10 volt supply, so that's connected there. And then we're feeding the slider of that preset through a 499k resistor to pin 1. Now normally pin 1 would be grounded, but because we're feeding an offset voltage in there, I've put a small resistance there, a 100 ohm resistor, from pin 1 to ground. Now because I've added a resistance there, I've upset the characteristics of this circuit, so to compensate for that I've added a 10 ohm resistor there, which compensates for the effect that that 100 ohm would have. So basically what you're seeing there is that the way the internal amplifier works, you have a 100k and a 10k that's at the gain of that amplifier at times 10. So if we add a 100 ohm in series with 100k, you can see by the proportion that's gone up by, and to maintain that level we simply put a 10 ohm in series with the 10k resistor input there. So that resistance there compensates for the fact that we added that one there, basically. So the way this now works is that we short the two leads here together, the input to the op amp. We then adjust the 100k preset there to zero the output, so we've got 0 on the output, 0 volts out. We have the resistance connected across the 100 milliamp constant current source. If we then have these two here, the sense wires from the differential amplifier connected across the resistance, because we've now zeroed it, it will accurately measure the voltage across that resistor and feed the output to the meter. Now you can either feed that to a normal multimeter, or in my case I'm going to use a little panel meter there, a 2 volt panel meter, 5-digit 2 volt panel meter, to give me the display. And but I will probably put some sockets on the back of the project box so you can also connect it to a multimeter. So basically that's the circuit that we have here today. Fairly straightforward. And what we'll do now is we'll build this up on a breadboard and test it, and just see how we can calibrate, and also how the zero offset there works when we connect the leads together. So let's put this. We have all the components now laid out on the breadboard for testing. You clearly see the 4 ICs I'm using. The first one there is the constant current IC, the LT3092. The one I've got here at the moment is a TSOT 6-pin version, which is very, very small and difficult to solder. So I think when I come to the final project, I'll use the SOT 223 version, which is a 3-pin version of the same IC. I'll just show you that. So, which makes it much easier to solder onto a printed circuit board. So I'll be using this 3-pin version as opposed to this 6-pin version you see on the breadboard there. Next to the constant current IC there's the the shunt regulator. It's the 1.25 volt shunt regulator IC, which is the LT1634. Moving on, there you have the Max 680, which is the voltage converter IC with its 4 capacitors, and in this case I'm using 4 tantalum capacitors, 4.7 microfarads. Then moving on, there's the differential amplifier, the precision differential amplifier. That's the INA 106 together with its associated resistors there. Those resistors there, and the preset is for zeroing out. And then finally on the right hand side of the breadboard there we have the 5 volt regulator IC, the LM2940, and the smoothing capacitor, the 220 microfarad on the output of that. And there you have the 6 batteries giving us our 9 volt supply. Just quickly at this end of the board, there you have the 7 100 ohm resistors, all 0.1% tolerance, and a 56 ohm resistor there in series with a 100 ohm preset where we can trim that down so we get exactly 12.5 ohm in combination of the whole lot there. And then finally, you see I'm using here a panel meter which I found on eBay. Quite cheap actually, these. This is a 5-digit panel meter, maximum reading 2 volts. So it's 2.40s, so it's going all the way down to 0.1 of a millivolt. So that should be quite good for us for this particular project. Now I've just temporarily connected 2 leads in here, the red and the black, what we'd use to supply the 100 milliamps to the unknown resistance, and the yellow and the green leads there, we'll use them, the sense leads, to measure the voltage across the unknown resistance and feed that to the differential amplifier there. So I think what we'll do now is we'll connect the 9 volt supply to the board. Well, there I've connected the power, so we've now got 5 volts coming from the regulator IC feeding the constant current IC there, and then the voltage converter IC there is giving us our plus or minus 10 volts. So the first thing we'll do is I'll just short the 2 sense leads together and see if we can zero the meter. The output, because the meter at the moment is monitoring the output from the differential amplifier. So what this particular panel meter is just connected to the 5 volt supply, and then the other 2 leads is then monitoring the output from the differential amplifier from ground to the pin 6. Well, with the 2 sense leads there from the input of the differential amplifier shorted out, I'll just adjust the 0 preset there and see if we can get the reading on the display down to a 0 reading. Going down, just take it a bit more. If I go too far the other way, we start going negative. So we go back and just zero that about there. So we've now got the differential amplifier zeroed out with the input leads to it shorted out. What we'll do now is we'll connect I've got a precision 0.1 ohm resistor here, so I'm going to connect that across the 100 milliamp terminals. And then I'm going to connect the sense leads going to the differential amplifier across it as well. So we put the green lead to the negative side, and we put the white or the yellow lead there to the right. That's now giving us a reading of 0.0972 of a volt. Now if we had precisely 100 milliamps going through a 0.1 ohm resistor, we should get exactly 0.1 of a volt. So let me just trim the preset here which sets the output current from the constant current IC. And adjust that for a reading of 0.1. Just about there. I'll just trim it a bit more. That's pretty close. Well, there we have. We have the reading now showing us 0.1 of a volt, and we have the 0.1 ohm resistor across there. So the reading is reading effectively the resistance because it correlates exactly to the resistance there. And the reason behind that is, remember, we had the times 10 gain of the differential amplifier. So that seems to be working quite fine. A little bit later we can probably test the actual current itself using a current meter just to see exactly what we actually have going through the resistor there, just to be on the safe side. But for now that seems to be working fine. Let me replace the 0.1 ohm resistor with a 50 milliohm resistor. That's a 0.05 ohm of a resistor, so let me just disconnect this. And we connect the 0.05 ohm resistor on here. And there you can clearly see the reading on the display there is reading 0.0499. So that's ohms effectively now. The voltage will equal exactly the ohms reading. So I think that's quite good. Pretty close to what that is, and certainly with the tolerance of that particular resistor anyway. And finally, let me just try. I have a Precision 5 milliohm resistor here from Vichy. Let me just see what that reads across the terminals. This is actually a current sense resistor of 5 milliohms, so it has 4 terminals, so we can utilize those. And there you go, that's giving us a reading of 0.0052 of an ohm. So yeah, it's 5 milliohms. So that seems to be working fine. Here you can see some of the other items I'm going to use on this project today. I managed to find some of these Kelvin alligator clips on eBay. Quite nice. It only cost me a couple of pounds, and this is quite good because you've got connections on both sides. They're insulated from each other, so you can have 2 connections on the same side. So I got a red one and a black one of that, and I also found on eBay some short leads. This is using I think it's 14 gauge, quite thick wire actually. It's quite nice, and it already has moulded onto the other end the 4mm banana plugs, so I got 2 of those as well. We're going to use some banana sockets there, different colours, and also there's the on-off switch. I'm going to use a little push button on-off, which is a latching push button. There again you can see the AA battery housing for 6 batteries, and I decided for this project I made a little printed circuit board for it. There you are, which will make life a lot easier really. I'll make the artwork for this available below on this YouTube video. Just looking at the project box, I got one a little bit deeper than I normally get. This is 80 millimeters high. Normally I get about 60, but because I'm using a panel meter which is fairly large, I need to get the extra height there, so that's 80 high. And the length of this one is probably a bit longer than I need. It's 185 millimeters, and the width across there is 135 millimeters. You can get these again on eBay for around £5, which is quite nice. And the actual lid comes off. It comes with feet inside, and the nice thing about it is that the front and the back panels will remove, so we can take them out, mount them up and cut them out and drill them to our particular needs. So that's quite nice, that. So I think what I'll do next is I'll take one of these panels, well both actually, because I need some sockets on the back as well to connect to output to the meter. But what I'll do on this panel here, I'll cut out a part there for the panel meter, and then we'll put some holes at the bottom for the banana sockets, another hole we need for the on-off switch, and I'll probably put a hole somewhere in the middle there for the zero adjust facility, because we may have to have access to that at the front of this this little meter. So let me go away and mark up and cut out the holes for the front and the rear panels, and we'll come back and have a look at that. Well, here you can see I've now cut out the front, and I put 2 socket holes there on the back for 2 wonder plugs. So we have all the holes now cut out. Let's just have a closer look at that. So that's the front panel with all the holes cut out. What I did there, I just put some white tape on there, marked up all the holes, and then drill these. And the cut out for the panel meter, I cut that out with a little Dremel, with a little circular disc saw on the Dremel. So let me now mount the components onto this front panel and see how that looks. Here we can see now I've got the display, the little panel meter there mounted on, the push on off switch, latching, and the 4 sockets on the front. The middle hole there I'm going to use to adjust the zero. So I think the red and the black one I'll use for the 100 milliamps output, and the white and the green I'll use for the sensing to measure the voltage reading and give me the reading on the display. And then on the back I've added the 2 banana sockets on the back there, and that's an external connection to an external meter. So if you didn't have the panel meter, you could just have an external meter, or you can use the external meter to also just check and see how it compares with the panel meter. The panel meter itself is a 2 volt 5-digit panel meter, and I purchased this one off eBay. I think it cost me around £6, this particular one. It's quite a large display, using 7 segment, but this one displays up to 2 volts. Now just looking at the other components, because we have the battery holder here, which I think I'll mount somewhere near the back there in the case, and then hopefully I can mount the printed circuit board between that and the front panel. I can do that, and I'll try and position the little zero pot so it's in line with the hole at this hole at the front. What I did do, I found a little sort of a knob in my junk box, which I'm going to use to connect to the zero control. So I've drilled a hole there which is sufficiently big enough to take that particular control pot. But depending on what you do, you can choose your own method for that. It doesn't have to be exactly like this. This is just something I had in my junk box. Well, that's more or less the positioning of the items in the project box. So I think the next thing I'll do is I'll mount all the components on the PCB with some wires, and then we'll come back and we'll have a look at that. Here you see now the printed circuit board with all the components mounted. I've also marked on the top there some indication on what's what. So I've got the 100 milliamp preset there, and the 0 set preset is down there. I've tried to keep that in the middle of the printed circuit board. The IC I'm using there, the Max 680, which is the voltage converter IC, I've put in a little 8-pin DIL socket there. And there you can see we've got the voltage regulator IC. It doesn't need a heatsink for this. And the rest of the board is really a few capacitors and the resistors. I've also mounted on the board the wiring output, so the red and black wire there is the 9-volt battery in, the black and the orange wire is the plus and minus for the current 100 milliamp supply, and the sense wires here going to the differential amplifier, green and yellow, and then the output going to the output sockets on the back of the project box is the orange and the green here. And then on the reverse of the board you can see I've mounted the surface mount ICs on this side of the printed circuit board. Let's just have a closer look at this. Here we can see the underside of the board, a closer look here, and you can see the 3 ICs I've soldered onto the print side of the board. There's the constant current IC, the LT3092, and as you can see now I'm using the SOIC 223 format, which is much easier to solder on the board. 3 main pins. The tab as well is soldered, which is also connected to the centre pin there. The IC next to it there, a little 8-pin surface mount IC there, is the shunt voltage reference IC, and then the other IC there you can see is the INA 106, the precision differential amplifier. Now on these 2 particular ICs, they're 8-pin, I've put a little dot on the printed circuit board there that signifies pin 1. And as you see I've marked some other detail on the print side of the board so we can see the negative 10 volt line or the plus 5 volt line and also the plus 10 volt line there. So I've marked on the outputs as well. Now let's just turn the board around and have a look at the component side of the board. There's the component side of the board. You can clearly see there the 7 100 ohm resistors. I'm using here 0.1 tolerance. You can actually get better quality ones than I've got here if you wanted to improve this, and that's entirely up to yourselves, but these seem accurate. And what I've found is that by using several 1 ohm resistors in parallel here, all of 0.1 tolerance, the overall accuracy of the tolerance of that is much better than 0.1. There we have the 15 turn preset to set the 100 milliamp, and there we have a 15 turn preset there to set the 0 of the differential amplifier. There's the voltage regulator IC, no heatsink required for this project. The main smoothing capacitor there, 220 microfarad, put a 16 volt working one in there, and then I've used 4 4.7 tantalum capacitors there for the voltage converter IC. The next thing I'll do now, I'll mount both the printed circuit board with the components on and the battery holder into the bottom of the case, and then we'll come back and have a look at that. Here we can see the printed circuit board now mounted in the casing. I've mounted it on plastic screws and just raised it by adjusting nuts underneath it. So it just slots on there, and I've aligned the 0 set trimmer so it lines up with the hole at the middle at the front panel. Now originally I was going to position the battery holder down there, but I realised that that's going to block access to the 100 milliamp set preset. So what I'm going to do now is mount the battery holder in the top of the case upside down. So in order to do that, what I've done is, if I look at the top of the case, I've cut a piece of aluminium and bolted that down with some screws onto those standoffs. You can see we've got some standoffs there at that side of the board. Well, we had 4 there, so I've just mounted it off those standoffs, and the idea then is I've just tapped some screw holes there for self-tapping screws, and then that will then screw onto the aluminium plate. So let me do that. So you can see now I've got the battery compartment now firmly fixed onto the top of the casing, so that will then hang down. That's the top of the casing, so it's out of the way of the 100 milliamp preset. Well, I think the next thing we'll do now is we'll connect all the wires up to the banana sockets at the front, get the meter connected, and get the on-off switch connected to the battery, and then the power leads joined up. So let me do all the wiring, and then we'll come back and have a look, and then we'll do a final test. I thought I'd just show you how I've connected the panel meter up there. It's a 4-pin plug going onto the panel meter. The red and the black wire are the supply voltages. So I've connected the red wire there to that point there, which is actually the plus 5 volts. That's where I'm tapping it off there. And then the ground there is just onto the ground in there. The output voltage, measuring the sense, I've got the positive there on the yellow wire on the output, and the blue is the negative return, which is actually the earth. So that's how we've connected the panel meter. That actually just unplugs, makes it easy then to install the PCB. Here we see everything's now wired up, the board's connected, the input terminals there wired up, the push on off switch is wired up. I've just put some heat shrink on the connections for the leads going to the battery holder there, and then the output leads here for the output meter is also wired up there. So I think what we'll do now is we'll box it all together, and we'll test it and see if it's working. Here you can see the unit now boxed up, and at the moment I've just left the back cover loose, so if need be, if I need to get to the 100 milliamp current preset, I can do that. The 0 preset is controlled by the knob there on the front, which I've simply just got a spindle going down onto the little preset on the PCB board. Here you can see I've got the leads. I've wired up the Kelvin alligator clips I had to those leads with the 4mm plugs on them, and red and black will plug into the current source there, that side, and there's the sensing input, so a red and a black onto the sensing input. So what I'll do first of all, I'll connect the wires up, and then well, before I do that, I'll just switch the meter on, see if it works. Well, that seems to be fine. There's no need to have a on LED on this unit, because clearly you've got such a bright display. If the display comes on, you know the unit's on. So what I'll do now is I'll connect the leads onto the input sockets there. I've now connected the leads, and as you can see now, the display is showing all H's, which is effectively error or overload feature, because at the moment we haven't got anything connected to the alligator clips, so it's open circuit. So if I simply first of all short the clips together, and we look at the reading, we should be getting a 0 on the display. In fact, we are at the moment, so I must have the 0 set more or less about right. But you can actually adjust the 0 set, and you can see there I'm getting some error there now. So if I just adjust that back again till I get to 0, about there, that's about 0 now. It's, the next thing we'll do is let's just quickly put a resistor across the inputs. I'm going to choose a 0.1 of an ohm resistor and see what that reads first of all. And that's given me a reading of 0.0992. So it's pretty close to 0.1 of an ohm, and obviously there's a tolerance on that particular resistor. That is a 1%, a 0.1% tolerance resistor. Now it could be that we need to just trim the 100 milliamp source current on this from the little preset at the back, and I might do that in a moment, but let me just check a few more resistors first. I'll put a 50 milliohm resistor across. That's 0.05 of an ohm, and there we're getting pretty accurate really. That's 0.0498 of an ohm, so that's 49.8 milliohms. Now let's take it down a bit more and check a 5 milliohm. We've got a 5 milliohm resistor there. Obviously the length of the, where I've got it on the leads, it's reading the resistance of the leads as well, but that's reading 0.0063 of an ohm, which is 6.3 milliohms. Let's just, for the hell of it, this is a 1 ohm resistor, 0.1% tolerance. Let's just see what that reads. And that's reading 1.0007 of an ohm, so pretty good. Right, well I think what I'll do next is I'll just check the 100 milliamp is set correctly. Right, here you can see I've got the unit connected to my Keithley 2000 multimeter here, which is quite accurate. And it's on the current range at the moment, so I've got the current inputs there, and I've just put the meter straight on the input current source there and measuring the current on the meter with nothing else connected, and you can see there it's reading 0.100044 of an amp, which I think you'll agree is 100 milliamps. Pretty accurate. I could trim it down a little bit and see if I could get those last few digits down, but I think at the moment that's pretty accurate, and I'm quite happy with that. Right, here we have the unit connected up again. I've got it connected to a 0.1 ohm resistor, and this time I've connected my Keithley meter on the DC volt range to the two sockets at the back of this unit, just to compare it with the reading we've got on this panel display meter there. And as you can see here, the panel display is reading 0.0995, and the Keithley is giving me a reading of 99.7. Here you can see I've got the unit this time. It's connected to a 50 milliohm resistor. That's 0.05 of an ohm, and the Keithley meter this time I've got it connected to the output terminals at the back of this unit, and I'm just comparing the reading on the Keithley with the reading I'm getting on this little panel voltmeter here. And what we can see is the Keithley's reading 50.1 millivolts, which implies that it's a 50.1 milliohm resistor, and the unit is displaying 0.0498, so it's suggesting it's a 49.8 milliohm resistor. So I think it's within tolerance, I think. Now, one other little point I'd mention is that on my unit here, the panel meter I'm using is specifically a panel meter that's got a maximum reading of 2 volts. I chose that because I could get down to 4 decimal places in the millivolts range. Which meant that I could read the resistance down to 100 micro ohms. But if you wanted to, say, let's say I put a 2 ohm resistor across the clips, the unit just simply shows over error, so you've got all H's. But if you connect a normal meter to the back terminals, you can still get a reading, and here we can see we've got 2.00185 of a volt, and that translates directly to ohms, so that will be 2.001 of an ohm. Well, I hope you all found this little project in designing and building this Milliohm meter of interest. I found it to be quite an accurate piece of kit really, and quite cheap to produce. This one cost me between £30 and £35, including the case. The unit itself is capable of measuring resistances from 0.1 of a milliohm, that's 100 microohms, all the way up to 2 ohms maximum. Well, if anybody's interested in having a go at building one of these themselves, then what I will do is I'll put a link below with the full schematic diagram, the parts list and the artwork for the PCB. Well, many thanks for watching, and if you found this of interest, please give me a thumbs up, and I'll see you all again next time. Bye for now.